So now I'm going to begin three talks on case control studies, one of the most useful of the epidemiology study designs. So in this, the first talk, I'm going to talk about why case control studies are particularly useful, and I'm going to illustrate that with some examples of the situations in which we might use them. And along the way, we're going to talk about things like particularly the odds ratio, which you've heard mention of, but we haven't really talked about what it actually is. But I'm going to try and explain it to you, and why it's such a really useful measure of association, a form of relative risk. So back to our familiar hierarchy of study designs, and this completes the picture here really. So case control studies, the last of the major study designs in between prospective and retrospective cohort studies. So case control studies, very basically, involve a group of people with a specific disease, a defined disease, which of course we call the case group, and then we have a comparison group without that particular disease, which we call the control group. And both these groups of people are selected from the same population. So it's very important to keep in your head that they're selected from the same population always. So, and then we compare the two groups, and we get estimates of the relative risk, which are the odds ratio, and we also have some other terms for case control studies. Sometimes that you see them referred to as case reference studies or case comparison studies. Both of those just basically case control studies. Most people use case control studies. Occasionally, particularly in the older literature, you might come across retrospective studies, and that is a term designed to confuse because, of course, it gets confused with retrospective cohort studies. So I strongly advise you never to use that one. And in any case, it's somewhat misleading because it suggests that we're collecting cases from the past, but as I'll explain to you, that's not the case. That's not the situation. It may have been in the old days, before case control study methodology was well developed, that maybe people did mainly get their cases that had previously occurred, so there was sort of retrospective studies, but it's not really the case anymore. So totally avoid using retrospective studies, but you may come across it in some of the older papers in the literature. So just to explain it at this point so you don't get confused. Now, the thing about case control studies, and one of the reasons why they are so popular, is that they can be considered to be a more efficient way of attaining information that might otherwise be collected in a cohort study. So I'm going to show you how that is the case. So, but before we move on to that, I'm going to talk about some situations where we would want to use case control studies. There's a simple way of conceptualizing case control studies and cohort studies together. And when I first saw this diagram many years ago, it was a kind of like a light bulb went on over my head. It really clarified things, and it's a way of thinking of the two study designs not as two completely separate entities, but two ways of really looking at the same population, but just from a different angle. So we've already talked about cohort studies, and you know that we usually are comparing an exposed group, the total of which is M1, and an unexposed group, the total of which is M2 people. So we can say, conceptually, we can think of a cohort study in terms of M1 and M2 being essentially fixed, and the question is, you know, how many A's do we get out of M1 and how many C's do we get out of M2? A and C, of course, being the disease cases. So if we look at it from the other angle, in a case control study, we're doing the reverse. Basically, we're fixing, you could say, the number of cases of a disease, and we're also fixing the number of non-cases, or controls, as we normally refer to them in a case control study. So it's basically just looking at the same population from a different angle. But our sampling strategies may be different. We may take samples for M1 and M2, we may take a sample for N1 and M2. So we sample differently, but basically we're still trying to get a handle on A, B, C, and D, and we're essentially investigating the same population. So two different ways of looking at the same population, even though the study designs are very, very different. We're trying to get the same answer ultimately, as you'll see. So we're going to talk about 5 situations when a case control study design may be particularly useful. And I'm going to start because I think it's a useful, it illustrates the connection between case control studies and cohort studies. I'm going to start with this situation here where exposure data are very expensive, or they could be very difficult to obtain. So we'll start with this example. It's similar to one that's in your textbook, but as I often do, I take the textbook examples and I modify them and extend them a little. So basically, we have the situation. We carry out a study. We're interested in whether pesticide exposure increases breast cancer risk. Then we recruit nearly 90,000 women in a prospective cohort study, and we follow them for 8 years. But as is typical in cohort studies, we collected blood samples from all the participants at the beginning of the follow-up, because we may not be entirely sure at the beginning of the follow-up what exactly we want to do with those blood samples, but blood samples are always useful. They have various biomarkers and things that we may give us a lot of information. So in this cohort study, over the 8 years, 1,400 or so breast cancer cases occurred during the course of the follow-up. And then we have a hypothesis. We might think that DDT, the major metabolite, the major product that it's converted into in the body, is DDE. So usually we don't look for DDT in people's bodies, we look for DDE because it's a more long-lasting form of DDT. It persists for quite a long time, at very low levels, of course. So we might decide to, based on some cut-off point, decide to divide DDE levels into high and low, and then examine the high and low levels in the cases in the cohort to see whether or not there's evidence of that DDE is associated with breast cancer. So here's our data. So this is assuming that all the blood samples were analysed. We used all the entire population of the cohort study. We divided them into those designated as high and low exposures, and we had the 1,400 breast cancer cases distributed between the high and low exposures, and then we calculated the relative risk for high DDE versus low DDE, and you can see that there's a relative risk of 1.88. So the problem is that if we had to analyze the blood samples of 90,000 people, that would be very expensive. So the solution that we adopt is we take all of the cases, 1,400 or so, and then we just take a random sample of the women who didn't get breast cancer, say twice as many as the cases. That's like 2,800 or so, and we call those the controls. So here we have our case group and our control group. And if we just use that sample, the analytic costs of the study would only be about 5% of based on the proportion of the total cohort that we investigated. Only about 5% of the cohort study analytic costs. So let's have a look at our data from the case control study. So here's our case control study. We have our cases and our controls here. And you can see there's the totals, 1,400 or so and 2,800 or so. And then, and this is how it would break down. We can predict that quite simply, given that we know the cases, we know how it breaks down, and if we take a random sample of the controls, it proportionates exactly as it would in the cohort study. So it's exactly the same proportions we found in the cohort study. So how do we calculate our relative risk? So we can try carrying out exactly the same calculation that you're already familiar with, and where we basically it's exactly the same method as we used to get the 1.88. So, but what happens then? We get 1.49. So that's not very good, because that is quite different to the 1.88 that we previously obtained. So how do we get around that? Because really, we're trying to use the case control study as a more efficient way of carrying out a cohort study, and if we just get 1.49, it's not the same as 1.88, so we need to do something a bit better. So this is where I need to introduce you to the odds. So the odds, leading up to the odds ratio. So the odds can be defined as the probability of something happening divided by the probability of it not happening. And a simple example is if you think of rolling a dice. The odds of getting a 6, so the probability of getting a 6, of course, is 1 in 6. And the probability of not getting a 6 is 5 out of 6. That should be obvious to everybody. So the odds of getting a 6 on one roll is 1 over 6 divided by 5 over 6. The odds of getting a 6, the probability of getting a 6 divided by the probability of not getting a 6. So that's 0.2. So that's the odds. The probability of an event occurring to the probability, the ratio of the probability of an event occurring to the probability of it not occurring. Okay. Now let's go back to the 2 by 2 table. It should be very familiar to you now. So just to remind you that of the A, B, C, D, this structure should start becoming completely intuitive to you, A, B, C, D. And then there's the row totals and the column totals. So let's talk about the exposure odds ratio. So if you think about the diseased cases, in other words, these people here, the diseased cases, then they have two possible outcomes for exposure. They can be exposed or not exposed. So the odds of being exposed if you are a case are A over N1 divided by C over N1. So let's have a look at that. So that's we're just talking about the cases here. So the odds of being exposed is A over N1, so it's the probability of being exposed, A over N1. The probability of not being exposed is C over N1. So we divide A over N1, the probability of being exposed, by the probability of not being exposed. So here we have it, A over N1 divided by C over N1. So the N1s cancel out, and we just get A divided by C. Okay. And so then we can think of in the same way about the non-cases or the controls. So they can be exposed or not exposed. So then we can calculate the odds of being exposed if a non-case or a control. So that is B over N2 divided by D over N2. Exactly the same procedure as we carried out for the cases, but this time we carried out for the controls. So that's the odds for the cases and the odds for the controls. So then if we want to get a ratio of odds, we divide the odds of a case being exposed, which is A over C, by the odds of a control being exposed, which is B over D, because when we carried out this calculation here, the two denominators in 2 cancelled out, so we got B over D. So you divide A over C, A divided by C, divided by B divided by D. And with a little bit of algebra, you can see that that comes to AD divided by BC. So that's a formula which we need to commit to memory. AD divided by BC. And we always think of it in relation to this table here. But you might say, well, what about if we accidentally flip the disease and put it on the other axis and the exposure on this axis? So in that case, let's think about the disease odds ratio. So we can carry out exactly the same exercise, but on the other axis. So if we start thinking about exposed people. So an exposed person can be a case, or it can be a non-case, or a control. And so then we can calculate exposed group disease odds. So this is how we do it. So we have the exposed group, and so the probability of being a case in the exposed group is A over M1. And the probability of not being a case in the exposed group is B over M1. So you can see we divide A over M1 by B over M1. And again, the denominators, which are in this case, the row totals, the row total being M1, just cancels out. So we get A divided by B, and then we can go through exactly the same exercise for the non-exposed group. So the disease odds there are C divided by M2, and all of that divided by D divided by M2. So we have that, C over M2 divided by D over M2. And of course again, the denominators cancel out and we get C over D. So then we calculate the disease odds ratio. We divide the odds of being a case if you're exposed, an exposed person, and divide it by the odds of being a case if you're not an exposed person. And so we have A divided by B divided by C divided by D. We do the algebra and it comes to AD over BC, the exposure, which is exactly the same as the exposure odds ratio. So the point here is that the disease odds ratio and the exposure odds ratio are exactly the same. So the implication of that is that it absolutely doesn't matter if you flip this table and you have this being the disease axis and this being the exposure axis, because basically it's just rotating on this axis here, and as long as you have the exposed case in this top upper left hand corner, as long as A represents the exposed case, then everything will fall into place. You don't need to worry about which axis you have, which is on which axis, simply because the exposure odds ratio and the disease odds ratio are identical. So that's a very convenient property of a case control study, that these two odds ratios are identical. Now that all probably sound like a very complicated explanation, and you'll never have to suffer through this again. But all I really wanted you to understand is that these two things are exactly the same. You don't need to worry about which one you're talking about, and it doesn't matter which axis, whether the disease is on one axis or the other axis, or the exposure for that matter. And just so commit to memory this little formula here, AD divided by BC, and always think of it in terms of a 2 by 2 table in which the exposed case is in the top left hand corner, the exposed case, and then everything else falls out from that. So remember, AD divided by BC. Okay, so that was the odds ratio. Now what is that? What's the importance of that in terms of our cohort study example? So let's apply, let's calculate the odds ratio for the data. Remember we took all the cases, we sampled the controls. So now let's calculate, now we know how to calculate the odds ratio, which is 360 multiplied by 2446 divided by 1079 times 432. I've got it slightly differently down here, but it all comes out to the same thing. So it comes out to 1.89, which is extremely close to the relative risk we got from our full cohort study analysis. So the point here is that by calculating an odds ratio, it overcomes this problem that we would have if we tried to calculate a risk ratio from case control study data. So it's a very convenient way of obtaining pretty well exactly the same result as you'd get if you carried out the corresponding cohort study. But at the same time, it's much more efficient because we only had to, in this instance, analyze 5% of the blood samples from the total cohort. So, odds ratios, they're very useful. They have a lot of several good properties, and they're commonly used in case control studies, but to some extent they may be used in other study designs, and particularly they are sometimes used in cross-sectional studies as opposed to calculating a prevalence ratio. But I've left talking about them till now, as they're not so intuitive as the other measures that we talked about, like the incidence rate ratio or the risk ratio. They take a bit of thinking about and a bit of getting used to. But provided that the cases and controls are properly selected, appropriate way, and we're going to be talking a lot about that, then they provide a very good unbiased estimator of the underlying incidence rate ratio in the population. In other words, if you were able to, if you had a lot more money and a lot more time, and you're able to carry out a cohort study, then you would expect to get the same result as you get from a case control study, which you can carry out generally, as I'll show you, in a much faster time. A couple of things, before I move on from this DDE example, a couple of things to note. And one of them is that the proportion of controls that are selected was pretty arbitrary. I just took twice the number of cases, but I could have done it in pretty well any other way. And the key thing is that you select randomly from the non-cases to get your controls. So I could have taken half the number of cases as controls, and I would have ended up with exactly the same odds ratio. It might have had some impact on the confidence interval, but we haven't really discussed confidence intervals yet. So it might, if you took a smaller number of controls, it might make the confidence interval wider, and a larger number will make it narrower, which is a good thing, but we'll leave that till we talk about confidence intervals. But anyway, the point here is that there's a great deal of latitude in terms of the number of controls you select. It doesn't have to be some ratio relative to the cases. It can be, as long as it's a random sample of the cases, then you'll probably be okay. And at the same time, we could have taken a sample of the cases, not just the controls. But it's usually the situation when we carry out case control studies that we have a shortage of cases, and so usually we end up taking them all. But in the cohort study we just looked at, there were a large number of cases, so it would have been quite reasonable to have just taken a sample, say maybe half or a third or something like that. That would have been. And if we'd done that and we'd taken just a sample of the controls and we calculated the odds ratio, we would have got exactly the same result. And you might want to actually try that out for yourself just to prove it. And it's fairly easy algebraically to demonstrate that that would be the case. Okay, let's move on to the next situation where case control studies are very useful. And that's the situation, which is actually pretty common, when we don't exactly know the total population that produced the cases. The boundaries may be kind of fuzzy. And we refer to that total population as the study base. And we sometimes say that we may say that it cannot be easily enumerated. This word enumerated, it really means that basically it means counted or listed. In other words, we can't identify all those people, and we couldn't make a list of them even if we wanted to. We don't exactly know what that population is. So you can think of the study base as basically the source population, and you can also think of it as the person-time experience, given that it's not like a static population in time. People are moving in time, people are coming and going, and so really it's more accurately thought of as a person-time experience, which involves people over time. And we sometimes divide the study base into two general types. Now the first of them is what we call a primary base, and this is a situation when we actually know everybody in the population that we're sampling from. Everybody is identified, and basically with the cohort study that we just examined, that was an example of a primary base. We actually know everybody. We can enumerate them, we can list them, so we know everybody there. And in a situation like that, it's relatively easy to carry out control selection, because we just take a sample and then we use them in our data analysis. So it's very straightforward. The only problem would come if you didn't have a way of kind of randomly sampling. And I mention here the term nested case control studies. We'll talk a little bit more about that later on. But basically, in a sense, taking well, really, in fact, not just in a sense, it was taking that case control study out of the cohort was really, that is an example of a nested case control study. It's a case control study that is drawn from a cohort. And nested case control studies can be thought of as having a primary base. The other situation, which is probably more common and in some ways more problematic, is having a secondary base. And so instead of actually identifying, or at least having a enumerated list of all the people in the underlying population, instead of that we start in terms of a secondary base, we start by with a bunch of cases that are identified. And they might come from a clinic or a hospital. And then we need to, starting from the case group, we then need to try and identify the population base that generated that case group. That's very important because we need to take the controls, as I previously mentioned, from exactly the same population. So to achieve that, and given that we don't exactly know what the population base is, we need to use some special control selection methods. So my second talk in this series on case control studies is going to be largely focused around control selection methods. And we may never actually definitively be able to enumerate the study base. In fact, normally we can't. So we don't set out to try and do that. We basically will set out to try and sample that study base without actually knowing exactly what it is. And it's a very powerful method for carrying out a study. So basically this is just the situation here. We have a 2x2 table with a bunch of cases and controls, but it's not really appropriate to add A and B because the sampling ratios are totally artificial. Ideally we would know what the population, the population, the number of cases in the population, and the number of exposed people in the population, the number of unexposed people, but we simply don't know this population. But the key thing is that we are able to generate a random sample of this population via controls. If we can sort of generate a random sample using some of the methods I'm going to talk about, then we can calculate an entirely valid odds ratio without knowing these numbers here. So the secondary base population, as I said, can be very difficult to define exactly what it is. Can't really draw a ring around it very easily, and people come in going from it anyway, as they are from most populations. So we just need to have a control selection method that can sample exactly the same base population as the cases, and we'll talk about that in some detail in the next talk. But I should also say that ideally we should get all the cases in the study base. So we're often very focused on getting the controls, but sometimes we're missing some of the cases. So we should make some efforts to get all of the cases, even if we eventually only take a sample of those cases. But as I said, usually cases are in short supply, and so we will normally take the lot. The third situation that I want to talk about when a case control study design can be particularly useful, when we have a rare disease, and a rare disease might be cancer or birth defects or Alzheimer's or Parkinson's, anything like that. There's no particular definition of rare. Some people would say it's anything less than 5% in the population. Some people might use a smaller number. And also, when a disease has a long latency period, and we've talked about cancer, and we know that the critical exposures often occur decades earlier than when the cancer is actually diagnosed. So the reason why case control studies are very useful in this situation is that cohort studies generally have to follow pretty big populations, and they have to be big populations if it's a rare disease. And so it's a big population followed over a long period of time if you're going to get sufficient number of these cases, such as cancers, to be able to actually sort of carry out some useful statistical analyses, because we really do need some reasonable numbers. But case control studies, simply by starting by defining a larger base population, they might take, for example, the state of California, and use a cancer registry, say, to identify and recruit all the incident cases, say in California, over a shorter period, which might be 1, 2, or 3 years, say. So they are very efficient in that sense. We can compress the time required, and we don't have to follow huge numbers of people because effectively the cancer registry, say, is actually following those people for us. Case control studies work pretty well if you're only interested in one particular disease, health outcome. But if you're interested in a wide range of outcomes, or you have an exposure which you're interested in, and you're not quite sure what it will do, you still may have to use a cohort study. Case control studies may not be sufficient in that instance. So they don't work in all situations, but very often they are very useful. So a case control study, this is the fourth situation. When you have a particular disease and you have multiple exposures that you're interested in, because you don't know very much about causes. So case control study can allow you to investigate multiple causes, potential causes, and that's useful particularly for a disease outbreak when you may not really have very good ideas about what's causing it. So if you remember, cohorts are usually focused around particular exposures. You identify an exposed group and an unexposed group, and you follow them in time, and you look to see what are the health outcomes that the exposures cause. So you can flip it around for case control studies. So you're having exposure of interest, you've got a disease of interest, and so you examine multiple potential causal factors, multiple exposures, to see if any of them appear to be risk factors. So it depends. If you're interested, if your focus is on an exposure, then you might want to do a cohort study. But if your focus is on a disease, then you might want to do a case control study. So case control studies, and this is a bit like cohort studies really. They can be population based, or they might be based within a special group. They might be based within say an occupational group, in which case they'd probably be referred to as nested case control studies, because they're nested with, say, within an occupational group, which might be maybe forming a cohort. So that's the end of the first talk, and in the next talk I'll go on talking about particularly about the various control selection methods that we have available to us.